Hey audience, I've got a new project that I want to get up and running pretty quickly. I want to build a sous vide. And if you don't know what a sous vide is, it's a temperature-controlled water bath, and you take whatever food you have, like a piece of meat, and you vacuum seal it and heat it up in this water bath to get it right up to the right temperature. So I went and got myself one of these guys. It's an immersion heater. You just shove this in some tank of water, and then you plug the other end into a wall, and it heats up your water for you. I don't know exactly what temperature it heats it up to. It does have a thermostat. That's this line right here. It's a temperature sensor and a thermostat up in here. So it does do its own temperature control, but I don't know what temperature it's set to, and it's probably going to be hotter than what I want. So I'm going to need some way to turn this on and off with a separate control unit, which I'll make out of one of these guys. Oh, also the water needs to circulate, so I've got a little submersible pump, and that can keep my water circulating inside my tank, and that also just plugs into the wall. So this little guy on its own is obviously not going to be switching wall current on and off, so I'm going to need one of these guys, a big old relay. This guy, let's see what it says on there. Yeah, it says it can switch 10 amps at 240 volts AC, and that's going to be more than enough for driving this heater, because this heater says that it will draw, what is that, 1,000 watts at 120 volts, so that's about 8 1/3 amps of current going through this guy. Now, unfortunately, the Arduino is also not going to be switching this guy on and off on its own. The coil in there takes 12 volts DC, which, I mean, the Arduino can't source anyway, and it'll take, according to the data sheets, 75 milliamps, I think, and the Arduino is definitely not going to be putting out that much current. So I'm going to need a transistor. So here we have a 2N2222. That should be able to handle enough current to switch that relay on and off. This data sheet for this transistor says it can handle about 800 milliamps of collector current, which is more than enough to drive that relay. So normally when you're driving a relay with a transistor, you'll want to put a reverse bias diode across the coil contacts, because when the relay is turned on, a bunch of current is flowing through that coil, and that current is going to want to keep flowing when you disconnect the power source. So that current needs somewhere to go, so you put a reverse bias diode on there, which normally doesn't do anything because it's reverse biased, but as soon as you disconnect the power, the current can flow through that reverse bias diode, and then that will prevent it from presenting any high voltages to the transistor that's driving it and breaking the transistor. A neat feature of this particular relay is that it has a little LED built into it. Whenever you remove the power source from the coil, that little LED lights up a little bit. That acts as the protection diode that's already built into this relay, so I don't have to add an extra protection diode to my circuit, which is kind of nice. Then I'm going to need a way to sense the temperature of the water bath, so I can know when to turn the heater on and off. So I got a few of these guys, which are apparently waterproof temperature sensors. They actually have a digital output that's over this one-wire serial interface. And there's a one-wire serial library for the Arduino that can handle that. And there's also a library made just for these temperature sensors that handles everything for us. So we don't really have to do much work for that, which is nice. So for the high voltage portion of this project, safety is kind of important, so I want to, especially since this whole thing is going to be, in my kitchen and stuffed into a big bucket of water, so I want to have a GFCI protecting both the heater and the pump. So the idea here is I'll have AC voltage coming in from the wall, a switch so I can turn it on and off, and then from there I want to go into a GFCI outlet. And this will provide protection for whatever is plugged into it, which would be, let's say, the pump, circulation pump. GFCI outlets also have a set of protected terminals that have the same line voltage on that's coming in, but anything downstream of these, anything that's connected to these terminals, will be GFCI protected by this outlet. So what I can do is I can take these and I can put those on the relay switch and then run that to just a regular outlet. And then this I can plug my heater into. And then the Arduino can actuate this relay and turn this whole entire outlet on and off. So at some point I might also want this temperature controller to cool things off. As long as I'm here building this now, I'm going to want, let's say, another one, a separate outlet that has a separate control that goes to the Arduino, and I can plug a cooler into this. Like say I could plug a refrigerator into this small refrigerator, and then if I wanted to maintain things at a colder temperature, I can use that as the output of the temperature controller. So I can have a heater, some kind of heater plugged into it, and some kind of cooler plugged into this one, and the Arduino will actuate whichever one of these it needs to either heat it up or cool it down to whatever temperature it needs to be set to. So this here is what I'll be building it in. It's just, I guess, a 4-space outlet box that's normally just get stuck into your wall. So I have space for a switch, space for the auxiliary outlet, which is the GFCI control outlet. This one will always be on as long as the switch is turned on. And then I have an outlet for the heater, which will only be on when the Arduino says heat, and an outlet for the cooler, which will only be on when the Arduino says cool down. It's worth noting that I found this out later, but there are these little tabs here on the outlets, and if you cut this tab, then you can power both of these outlets independently of each other. So you could, if you're doing this yourself, which I would not recommend, you could cut these tabs and then have one of these be the heater, one of these be the cooler, and then you would only need a 3-wide box instead of a 4-wide box. But as long as I have this set up, I might as well, plug a heater into one of these and then plug something like a lamp into the other one. So the lamp will light up whenever the heater's turned on, so it's a nice little indication of what the controller is doing at any point in time. Now in order to wire all this up, I got a bunch of 16-gauge wire. This was a mistake. If you decide to try and build one of these on your own, which again, probably not the best idea, pay attention to the number of strands in the wire that you're getting. This is 1619, that means 16 gauge and 19 individual copper strands inside the wire. The problem with this is that stranded copper wire cannot carry as much current as solid copper wire. And in fact, this 16-gauge wire, according to some cursory research I did, is actually not rated to carry more than like 7 amps, which is, less than what my heater is going to take. So this is a bad idea. You would be fine if you used 16-gauge solid core wire, or if you drop down to 12-gauge wire, but I'm just going to use this anyway because it's what I've got and I don't want to go back to the hardware store. But yeah, don't do this. It's a bad idea. Now there's really not much space inside here to fit the relays into, because the bottom of the box isn't flat, it sort of tapers in. But I'm going to have to put these relays in upside down to make them fit. And I'll plan on securing those with hot glue, which is a bad idea, and don't do that. I'm only doing it because I am not a smart man. And the reason for that is that anything that we plug into here is going to be drawing quite a bit of current, and especially with these wires which can't technically or aren't rated for handling that much current, things are going to heat up a little bit, maybe. And that could melt the hot glue, and things could come loose and start bouncing around, and that's going to be a bad day for everybody. Really should find a better way of securing these, but I'm not going to worry about that right now. And the same thing goes for attaching a power cable to this. I'm just going to use one of these old power cables for it. I don't have the plug that takes this that I can add into there, so I'm just going to cut the end of this, pull out the strands, and solder them onto all the wires that I add myself, which is also probably a bad idea for heat reasons again. So that's the plan for now. At some point I'll come back here and replace all of those 16-gauge stranded wires with either 12-gauge wire or some solid core wire. I'll worry about that later and just get this up and running for now. I'm using the same color coding you'd see in the wiring in the walls here in the US. Black for hot, white for neutral, and green for ground. You'll also see bare copper wire used for ground.
I'll start by wiring up the hot wires. One from the switch to the GFCI outlet. One side of the GFCI outlet is labeled hot for the hot wires, and one is labeled white for the neutral wires. And the top ones here are labeled line, that's the input coming from the mains. And the bottom terminals labeled load are where you'd connect more outlets to make them GFCI protected as well. Two wires can get stuffed into the hot load section, and those can get connected to relays. Once I find out which terminals of the relays are the normally open ones. I want these hooked up to the normally open contacts on the relay, so whatever heater or cooler I have plugged in will always be off as long as the controller is off. And if something goes wrong and kills the controller, it will fail in a way that shuts off the heater and cooler, which seems a bit safer. The other side of the relay switch gets connected to the hot side of one of the outlets. I need to twist these guys as I put the wires in to keep the stranded wires from fraying. This really needs to be done with solid wire. Then the white neutral wires need to be run back from the controlled outlets to the GFCI outlet's load terminal. Only one side of the circuit, hot or neutral, needs to be run through the relay switches and then the on-off switch. And the hot wire is really the only safe wire to switch. It would technically work if you put the switches on the neutral wires instead of on the hot wires, but then when it's switched off, you'd have wires connected to mains voltage and you'd be the path to ground if you touched the wrong parts. Then some wires with the relay coils. These don't need to hold mains voltage or take mains current, so they can safely be made from thinner wires. Then the green ground wire is connected between all the grounds on all the things. And then I can finish off the high voltage part by cutting open this power cord and putting the hot wire on the other side of the on-off switch, the neutral wire on the other side of the line terminal on the GFCI outlet, and the green ground wire gets connected to all the other ground wires. The wires inside this power cable also look like 16-gauge stranded wire, which is probably not good. Then this whole mess needs to get stuffed inside the box. I completely gave up on getting the relays or power cable attached in any way and just kind of stuffed them in there. This is probably a bad thing.
Alright, here we have our definitely very safe temperature controller box, minus the controller. So for a smoke test, I'm going to plug it in, see if it blows up. Alright, so far so good. Now, turn it on. Well, it's not the worst thing in the world. These should always be on. That's not good. Oh, there it goes. GFCI was tripped. Alright, so the auxiliary port works, and then the heater port over here should only work when this relay gets tripped. Hey, there we go. And if the GFCI gets tripped, yeah, then the heater should shut off. Perfect. I think we're good to go.
I ran into an interesting problem while testing the controller portion of it. When I run it in the kitchen, I power it with my bench power supply, since it gives me both 5 volts for the Arduino and 12 volts for the relays. When I dip the temperature sensor in the water bath, the temperature reading gets messed up and I get a measurement of negative 196 or so. I traced this all the way back to the one-wire interface itself getting messed up and not just the temperature readings. The most obvious guess was that the sensors weren't entirely waterproof, but I never had any trouble getting temperature readings from a water bath when I had it powered over USB from my laptop, only when I ran it with the bench supply. So the power supply has lots of outputs with different voltages, which all share the same ground, but the supplies are isolated from the ground of the power outlet. So I think these floating outputs have lots of noise on them from the power supply. Normally that doesn't cause a problem since the supply and the ground have the same noise on them and there's still a stable 5 volts or whatever between them. But the water bath is a little bit conductive and has a lot of, I guess, charge mass? You can add or remove some electrons without changing its voltage very much because of just how many electrons are in there available to move out of the way or take their place. So the voltage of the water bath is very stable, and even if the probe is waterproof, the waterproofing ends up being the dielectric in a big capacitor, so the probe has a capacitive path to a very stable ground, and this was removing the noise from the floating power supply on either the supply or the ground, but not both. And this caused the power supply noise to actually show up over the temperature sensor, which prevented it from working. I have a separate terminal on the power supply that's attached to the wall power circuit's ground, so shorting that out ties all of the outputs to a stable ground at the power supply, removing the noise at the source. Then I have no trouble getting stable temperature readings. This is the only thing that made it work. Capacitors across the output of the 5 volt supply didn't help, I think because the noise was common mode to both the 5-volt and the ground terminals. But that's just a guess as to what's going on. In any case, I found it interesting, something to keep in mind for future projects.
And with that, my kitchen sink is a fully functional Sous Vide. If we zoom in on the display, it looks like it's slowly heating up. It'll get there eventually. I believe in it. The controller is pretty simple right now. We just have a very basic thermostat style control, which is just number too high, turn off heater. Number too low, turn on heater. So no fancy PID controller at this point. That's it. Now I have a fully functional sous vide that I can use to cook some fancy steaks, or in this case, develop some color film. It turns out if the developer is not at exactly 102 degrees, you are not getting your photos. But this time should work out a lot better than last time. So that's a fun little weekend project. Again, I don't recommend doing this. Don't do it, it's a bad idea. But it was fun. Maybe I'll do a follow-up at some point. I'll see you then.